Check, check. Okay, there we go. For some reason, OBS wasn't recognizing the microphone, and I had muted the really crappy microphone that's built into my webcam, so it wasn't picking me up. So I had to reboot it so that it would recognize it, and we're good. Charlie Mike, of course, that's my dad in in the chat there. So, uh, are we getting an echo? I'm hearing echo, echo, echo. Oh man, let me know if the audio clears up or gets better at all. Because if it's echoing or acting weird, then we might have to address that too. Not on my end. Okay, cool. And the viewer count is picking up, so that's awesome. Before I get into my usual opening announcements, I just want to say real fast that before the stream, my dad, Charlie Mike in the chat there, oh, he had it on the phone and the TV, so he was getting the audio from both sources. That makes sense. Um, he let me know before, while I was running into the door, I saw he'd messaged me on Facebook. My last live stream got over 1,600 views, which I usually average about 100 or so. So I had 16 times the usual traffic. I don't even know 1,600 people, so I don't know most of the people who watched my last live stream. It's a very small channel. I got 100 subscribers. Trying to grow it, obviously. So to have my last video hit 1,600 views is awesome. I hope that's a trend that continues. Obviously, the topic was very, it was very topical. It was something that a lot of people were very interested in. We were talking about the James Webb, so I'm sure that drove a lot of traffic. I might consider doing more themed episodes in the future because that one and the Galaxy episode I did previously both did really well. Um, but I'm just super thankful that 1,600 people took the time to watch my video, and one person took the time to click the little button to indicate they didn't like it. but um, but most of the people, I guess, liked it. Hopefully, and yeah, I just think that's really cool. And for those of you who are here already watching the show, I'm glad you're here as always. So I'm gonna do a little bit of housekeeping like I usually do, and start things off by making a couple of quick announcements about my astronomy club. You see behind me here, I've got our website pulled up. Uh, if you somehow don't already know, I am the membership director for the Northeast Florida Astronomical Society. We are the astronomy club here in Jacksonville. So if you live in the greater Jacksonville area and you are interested in astronomy, we are the people to check out. We do have club memberships. You can join by going to membership and then clicking join NEFIS. This is if you want to be a part of the community and you want to support what we do. We are a nonprofit. We're a 501c3 educational nonprofit. So here you can hit new membership or renew if you're up for renewal. Fill out the information, obviously, and all that. Our memberships are annual. It's $20 for a student or someone over 55 years old, $40 for an individual, or $50 for a family. And for us, a family is any two adults and whoever they happen to be in charge of. We don't get super specific about what a family is. All families are welcome in NEFIS. We also have a benefactor level for people that just want to give more. You don't really. I always tell people I'm the worst salesman. You don't get anything extra for being a benefactor. Your name is mentioned in the newsletter. That's nice. But really, it's just for people who just really believe in what we do and they just want to give more, but don't feel like you've got to. Individual membership is fine. And again, these are yearly, so you pay once a year. Where else can you pay $20 for an entire year of being a part of something, right? If you're a student, or 40 for an individual. I'm going to bring up our calendar real fast and talk about some of the events our club has coming up. We just recently had, 2 weeks ago, we had our Hannah Park Stargaze. It went really well. We had a really big crowd. Everyone had a great time. I got my new laser pointer, which is something else, I gotta tell you. Oh, if I thought my last laser pointer was strong. But we had a great time, and people really enjoyed themselves, and we got to see Saturn. Saturn's coming back into the sky now. We'll talk about that in a bit. In addition to some other objects, Ring Nebula, some galaxies as well. This Saturday and next Saturday are close to last quarter and new moon, respectively. So those are going to be dark sky observing sessions. I always tell people the dark sky observing sessions are not outreach events as such. They are our inwardly focused events. So this is for us to get out and make our own observations. That's not to say that it's exclusive or it's only available to club members or anything like that. It's a public place. There's no, first of all, we couldn't tell people not to go if we wanted to, but also we want people to join us out there and have a good time. Just bear in mind that, it's not going to be like at Hannah Park where, hey, come look through the telescope or whatever. A lot of us may be doing our own observations and may not necessarily want you to come look through the telescope while we're trying to do our own thing. That being said, though, you will often find that people are friendly, and it's not uncommon to be invited to the IVs. But if you do want to get somewhere nice and dark and use your own equipment, or just look at the Milky Way, or even just use a pair of binoculars, it is honestly a really great time. And it is somewhere, like I said, very remote, very dark. We observe strict light discipline. That means no lights that aren't dull and red, to preserve our night vision. Like I said, it is a serious observing event, but it is still one that people are welcome to come join us. Also, there's no bathroom facilities and mosquitoes everywhere. It is the middle of the woods. So that's this weekend and next weekend, those 2 Saturdays. If you are a member of NEFIS, you get emails from me periodically, and I like to let people know when I'm going out there, because I will meet them at the Firehouse Subs in McClenny, and then people can follow me to the swamp, which I highly recommend if you're going for the first time, because it is very remote and it's very easy to get lost trying to find it. And there's no cell service out there. Coming up next month, we are going to have, on the 3rd, very first Saturday of the month, is going to be our next Hannah Park Stargaze. And it's going to be a private Stargaze at a neighborhood. I try to do all of our Hannah Park Stargazes. I really love doing the Hannah Park events, but I can't be in 2 places at once. And Pine Ridge historically has been one that's been kind of my gig. I like to go do it. I've built a bit of a rapport. So I'm going to be at that one. I won't be at Hannah that Stargaze, but hopefully the following month I can take a look ahead and see for October. I'm not double booked. So October I should be there. Looking like it might actually be a decently busy month in September. Let's see here. Actually, no, it's all the same stuff, it looks like. We have our board of directors meeting on the 12th. And then our general meeting is going to be on the 9th of September. That's open for everybody. You can come to the general meeting. Board of directors meetings are open to the board and club members. But if you want to come see how the sausage is made. And then, of course, the 15th would be the 3rd Thursday in September. So that will be my next 1,000 Shimmering Lights live stream. Okay, let me take a quick look at the chat and see if any conversations have built up while talking. Scott says, howdy, Dave. Howdy, Scott. Looks like we have about 3 or 4 people watching right now. I might be one of the people watching, because I do keep up the stream in another window as well, so I can monitor how it's doing. But let's go ahead and get into it. I also, real fast, sorry, I just don't want to leave it out. If you live in the St. Augustine area, the Ancient City Astronomy Club, their website's down right now. I talked to their president. They're working on it, but they are another great astronomy group, and I don't like to do anything like sniping people away from them. So although I like to present our club as an option, if you do live in the St. Augustine area, by all means check them out as well. They're a fantastic club, and like me, you can be a member of both. Okay, now let's talk about astronomy. So I'm going to go ahead and put this away real fast, and I'm going to bring up Stellarium. Stellarium giving me grief again? Give me a second. These have been... Okay. Hold up. And there we go. Okay, got it back. Not sure what happened there, but hopefully you guys can see Stellarium. Let me just take a quick look at the live stream. Yes, it's there. Awesome. Okay, so Stellarium is the planetarium software that I use. It is free. They don't sponsor the channel or anything, but I like to let you know where you can get this wonderful tool that I use. It is available in 2 forms. There's a downloadable client, and there is the web browser version. I actually think the downloaded version's better, but doesn't seem to stream as well for some reason, so I use the web version for these live streams. But either one is a fantastic free resource, and it's made by and for astronomers. So you see this little oval over here. If I click that, That's the Andromeda Galaxy. So the deep sky objects and various things you can look at, there's Caldwell 20, are actually labeled in the software. It's meant to be used to plan an observing session. So it's a very thorough catalog, not just a sort of gimmick. Also, you can switch out your location to anywhere in the world, and you can come down to the bottom right corner and you can time travel, which means that using this software, I can discuss anything from any time of year. So we are not limited to just right now in August. We can go to wherever if you want to talk about something in the wintertime, in the summertime, or what have you. Speaking of, I want to quickly say before I dive in that this is what I call a live YouTube planetarium show where you are the planetarium director. So the whole idea of this live stream, and tonight's live stream does not have a theme, is to talk about whatever you guys are interested in. So I'm always able to just talk for 2 hours. That's never seems to be a challenge for me, but I prefer to talk about the things you want to learn. I like to hear from you guys. If you have a question, put it in the chat. There is no such thing as a dumb question. Every question comes from a place of not knowing something and wanting to learn. That is an honest question. A question that comes from a place of not wanting to learn would be the only thing I would consider to be a bad question, like a gotcha kind of thing. But if you genuinely want to learn, it's always a good question. And I let the chat and the questions drive the discussion. So as I'm talking, if anything pops into your head, just throw it right in the chat. I may not see it immediately, but I try to talk about all that stuff. If you don't have a specific question, you can also just post a topic. If there's just an idea or a concept in astronomy generally that you're interested in, even if you don't have a particular question, and we can talk about that topic. So with that said, let's talk about the sky tonight. So this is the sky as we're going to see it tonight. I'm looking to the north right now, but of course I can give us the whole panoramic view. And one thing you'll notice immediately is Saturn rising in the east. So it's getting to be about Saturn time. And in fact, I can check in a second when the opposition is actually going to be. But Saturn is returning to our sky. So if you look to the east, you may see a very bright star just above the horizon. I'd say about, let's get the grid here. Get the azimuthal grid. Here we go. Look at about maybe 20 or so degrees above the horizon. Let's see, are these 10-degree increments? 15, I think these are like 15. So maybe like 30 or so degrees. 10 degrees, if you don't know, is your fist at arm's length. So about a couple of fists above the horizon, you should see a very bright star. That is Saturn. If you have any form of optical enhancement, even just a pair of binoculars, it's worth it. You can make out the rings in a surprisingly low amount of power and aperture. I always like to remind people that Galileo saw the rings, and your average pair of binoculars is like 2 telescopes strapped together that Galileo wishes he had. So even a pair of binoculars is going to show those rings to you. But other than that, let's talk a little bit about some of the constellations in the sky, and I'm just going to peek the chat real good. Congratulations on 101 subs. Yeah, I am excited about that. 101 subs, that's pretty awesome. August 14th was the opposite. We had opposition of Saturn already? Man, I have not been paying attention, you guys. I'll talk in a second about what an opposition is, if you guys are curious. Say so in the chat. But Saturn, yeah, I guess we crossed opposition, so now is a great time to observe Saturn. We have, if you look to the south, you'll see this reddish star Antares. And I'm going to start there with the virtual sky tour. So Antares is a red giant star, which means that it's swollen up, cooled down, and turned red, and it's going to die. Right? Stars swell and they turn red when they're near the end of their life, when they run out of hydrogen fuel, and Antares is in that state. If you find Antares, you'll see these two other stars, Alniat and Tau Scorpii, form a sort of slightly bent line with Antares, right? It's not a straight line. Antares is a little off-center. It's like a little bit of a curve. Also, you'll notice across from Antares, Acrab, and I don't know if I'm saying these right, Acrab, Dashuba, and Pi Scorpii form a second curve. So you get two curves like this. And personally, for me, that's the easiest way for me to find Scorpius, right? I see Antares, I see a curve that includes it, a second curve, and now I've found this sort of blob over here, which to me forms the body of the Scorpion. If you take the curve of Antares and you keep following it, you hit another bright star here, Epsilon Scorpii. You keep going, you get to Mu Scorpii, not Caldwell 76, the star that's next to Caldwell. It's not letting me. This guy, Zeta Scorpii, Eta Scorpii, Sargas, over to Iota Scorpii, Kappa Scorpii, Lesath, and then it sharply turns to Shaula, and not that NGC object, but G Scorpii. So you see this curve kind of comes around, and then whip real fast to like a little sharp, right? And that is the tail and stinger of the Scorpion. If I add in the lines, you can see this sort of thing. Whoever drew these lines chose not to include G Scorpii, but to me, that's the stinger. You can have a Scorpion without a stinger, man. I mean, granted, our Scorpion doesn't have claws. We have to kind of imagine his claws coming out here and here, but you gotta have the stinger. To the left of Scorpius, you'll see this teapot-shaped asterism, and when I did the Hannah Park thing last time, I got a really big laugh because I pointed it out with the laser, and I said, do you see how, here we have the kettle with these 4 stars here. And I said, and there's a spout coming out this way. And then coming out this way, we've got a handle, right? And we come up here, and we've got, it even has a lid, right? There's a lid on our teapot. This shape could not be any more of a teapot. It is so plainly a teapot. It is a very distinct, easy to find. These are all very bright stars, by the way. So the teapot just announces itself, even from a dark, a light polluted sky. So obviously, this is a centaur, right? Clearly this is a centaur holding a bow, because this is actually part of the constellation Sagittarius. The teapot asterism, and an asterism is just a pattern of stars. It's not an official constellation. The teapot asterism is the easiest part of Sagittarius to see, but as you can see, the asterism does extend to some of these neighboring stars. And if I add the artwork, I feel like even the guy who drew this picture was like, I'm just going to draw a centaur and lay it on top of the lines because I don't know where it's supposed to be in this picture. This little thing coming off, he's like, maybe he's got a cape. I don't know, right? Somehow somebody saw a centaur in this pattern of stars. But that is Sagittarius. This whole section of sky, first of all, this is the core of the Milky Way. As you can see, the Milky Way widens right here. So this is the thickest part of the Milky Way. So if you get out somewhere nice and dark, that's where you're going to really see the Milky Way with your unaided eye. It's going to be very obvious in that piece of sky. If you get somewhere dark enough, the Milky Way will even widen out as you get there, just like you see here in the software. But also, this piece of sky is really good for observing a few of the best deep sky objects. Some of the brightest and best deep sky objects are found here. Certainly some of the best that the summer sky has to offer. Of particular note, we have a couple of nice open clusters, Messier 6, also called the Butterfly Cluster, and Messier 7, also called Ptolemy's Cluster. I like them because they are as different as 2 open star clusters can be. You really get the gamut of the sort of loose association of a few really bright stars, something like the Pleiades in M6, and then M7 is a very dense region of all somewhat fainter stars that almost feels like you're looking at a globular cluster. It really is kind of the bookends of the 2 extremes when it comes to open star clusters. M8 is one of my favorite objects ever. This thing is so cool. It is it's called the Lagoon Nebula, and it is a nice bright nebula. You can really see structure in it, which is rarely the case with nebulae. Usually when you're looking just with your eye in a telescope, it's just a tiny smear, but this one you can actually see some structure. It's very cool. The M24 star cloud, which is not actually an object as such. What it actually is it's a lack of the interstellar medium that normally blocks our view of the stars behind it. So there's actually more stars in this piece of sky than you can normally see because the interstellar gas and dust, what we call the interstellar medium, is sort of attenuating that light. The light shining through it, kind of like shining through fog, and the more distant stars are dimmed to the point of not really seeing them. But there's a gap in that cloud. There's an area where it's of low density, almost not quite, but almost a hole in the interstellar medium, and we can just see clean through it to an area that just looks like it's absolutely loaded with stars. And we call that the Sagittarius star cloud, also called Messier 24, which the software is showing here. But these regions where there's fewer stars all around it, in reality, there's just as many stars there. We just can't see them. But also, where is it? If I look around, I might find... Maybe if I zoom out... Let's search for it. Messier... Is it 18? I always forget if it's 18. Messier 16, the Eagle Nebula. That's always a good one, too. That's where the famous Pillars of Creation, if you've ever seen that picture. Again, if any of these topics interest you, throw them in the chat. We can dive into any of this stuff. The Swan Nebula, also called the Omega Nebula, also called M17. That's what it is. M18 is actually a star cluster, but M17 is the Swan Nebula. This one, again, very bright, easy nebula, shows a lot of structure, looks just like a swan swimming across the surface of a lake, or a duck. I think it looks a little bit more like a duck, but it's very cool looking. It's a very, very cool nebula and an easy target, again, for amateurs. So nebulae are often very challenging observing targets. They're often really, really faint, really difficult to see, barely a smudge. So the fact that we've got two really bright, really good nebulae with a lot of nice structure in them right in the same piece of sky is one of the things that makes, actually three, because we've got M16 as well, the Eagle Nebula, makes this a great piece of sky for a nebula nerd like myself. But there's another one out here, which is M20. Which is the Trifid Nebula. It's actually right by M8. I just kind of skipped right over it, which is a better example of what nebulae are usually like. It just there's a couple of bright stars here, and the stars look a little hazy, almost like they're shining through fog. But with decent equipment, you can sometimes tease out dark dust lanes going through the nebulae. But for the most part, these are going to be more of your very difficult, faint smudge kind of nebulae. But still, a great piece of sky for hunting nebulae, but also a great piece of sky for star clusters. We've got a lot of globular clusters and the like. I could probably spend a whole episode talking about Sagittarius, Scorpius, Ophiuchus piece of the sky. Ophiuchus, I'll just show you real fast, is this constellation nearby, which some people say Ophiuchus should be the 13th star sign, if you're into that kind of thing, because the sun actually does go through Ophiuchus in certain parts of the year. And Ophiuchus is also loaded with globular star clusters. It's a bit of a more of a challenging constellation to find, though, I will say. You got to get somewhere dark, and the stars that make it up are not much brighter than the other stars around them, so it's a bit of a challenge to pick it out from the background. Scott says there's a pretty pair of binoculars. I think he's talking about M8 and with a little lagoon in the Trifid. Yes, that is true. The Trifid in a pair of binoculars, if you're somewhere really, really dark, again, is a little bit of blurriness next to the Lagoon Nebula and makes a nice pair. I'm asked in the chat, have I ever heard of Universe Sandbox? Not only have I heard of it, it's in my Steam library, and I want to get a better graphics card so it doesn't crash my computer when I run it. For those of you who don't know, Universe Sandbox is I guess a game is a bit of a stretch because there's no like goals or anything to it, but it's a little bit of software you can get where you can go in and you can basically create your own stuff in the universe. So you can take like a star and like set its parameters, and then you can like put a planet orbiting around it. And you could just go buck wild. You could just throw comets at your planets and destroy them. You can have two stars collide or whatever, and you can really do a lot of cool stuff and set up some nice little simulations and just play around with playing God basically in this game and manipulating astronomical objects. But it is a little bit rough on the old graphics card. Oh, I'm blanking on the name right now. Son of a gun. Cooper. Cooper. I know his name. Cooper's saying in the chat that he got a planet to orbit at 60% of light speed. Yeah, that I'm pretty sure would obliterate a planet in real life. You must have put it in orbit around a black hole or something. I don't know how you got it going so fast. All right, so I will say that when it comes to the questions in the chat, I would prefer if they are of scientific topics, although that's pretty on topic. But we want to talk about things like planets, galaxies, things that we want to learn about astronomy. While I'm in this piece of sky, I will point out one other thing, which is Comet Kilo 2 Pan-STARRS, 2017 Kilo 2 Pan-STARRS. If you don't know how comets are named, long period comets get a C, and then whatever year they were found in. If multiple comets were found in that same year by the same person or observatory, they start to get these little letter number combinations, which I'm not 100% on how they assign those. And then the name of who discovered it. Pan-STARRS is like an automated thing that looks for comets, so that's why you see a lot of these Pan-STARRS. It's an abbreviation for something. I forget what it is. So I think it's interesting, though, that when an automated telescope finds a comet, they name it after the telescope, not the guys who own that observatory, like you would maybe think. So that's a nice little bit of no ego on behalf of whoever it is that operates Pan-STARRS. Or maybe it's a team, and that's why they do that. I don't know. But there's a little comet there. It is currently at magnitude 6.75, which is equivalent to the faintest stars that you can typically see under a decently dark sky. So if you get out somewhere nice and dark, you can see things at 6.75 magnitude. However, comets are not a point light source like a star is. That magnitude is smeared a little bit. So it's a little bit misleading, but still, a 6.75 magnitude comet is easily accessible in amateur scopes if you get somewhere dark enough for the background sky glow not to overpower it. So that's an object you can look out for. It's right off of the edge of Scorpius here, and I need to observe it at some point because I am trying to observe comets. So that would be nice for anyone out there working on comets. Comets are like cats. They have tails and they do exactly what they want to do. So they can be difficult to predict. And so anytime we get a decent comet, it's always a nice treat because you never know when you're going to have one, right? Sometimes they just flare up real bright, and sometimes you think they're gonna and they don't. So with comets, you just take what you get, man. All right, moving around a little bit in the sky. Pegasus is coming up, which means that we're going to start to get access to Andromeda and the Andromeda Galaxy. Still kind of low in the sky, but look for it in the next month or two. It's going to be much more prominent, or stay up later, right? You can always, if the object you want to see is low in the east, you can just wait for it. It'll come up, right? As it does, it's going to be bringing up Jupiter as well, so that's exciting. Jupiter, by the way, is my personal favorite planet. If you guys have ever been curious what my favorite planet is, if I haven't talked about it on the show, it is Jupiter. And, oh, look how close the Moon and Mars is. That's a nice conjunction, too. Let me time travel a little bit. Now I'm making my own topics. I'm just sort of looking here. I'm curious. Oh, you know what? I shouldn't jump ahead month by month because that'll change the moon's position, right? But let me look day after day. Oh, okay. Let me time travel a little bit. Look at that. So, oh man, but you'd have to be up really late. This is like 5 a.m. that I'm showing right here. 3 a.m., 2 a.m., 1 a.m. But man, if you wanted to get up after midnight or stay up late tonight, I might try for it. That's a nice conjunction of the moon and Mars. A conjunction is just what we call it when two objects are close to each other, right? You get two objects passing really close by. That's a conjunction. An occultation is when one of them, typically the moon, blocks the other, right? So as I time travel here, you'll see that the moon is going to pass next to Mars. It does not occult it. If that were an occultation, I would definitely stay up for it. Those are always cool to watch. So that's something coming up as well, but that's not really going to be super available to us tonight. But around 11 o'clock midnight, Jupiter is going to come out as well if you want to stay up for that. All right. I'm going to check the chat again for any questions or anything. And hey, okay, there we go. Angie and I are watching. So Andrew and Angie are watching. That's awesome. Andrew, I meant to get back to you about hanging out on Friday. I will get back to you after the live stream, but basically the short version is there's something really cool happening on Sunday, so I thought we could do that instead. But anyway, so let's see here. It was inside. My answer to the previous question about the planet going 0.6 C. He said it was inside a black hole. Well, there you go. That'll do it. Okay, so other things to observe in tonight's sky. If I get back to 20 is 8 p.m. 20:55. This is like 10 p.m. or 9 p.m. So this will be 9 p.m. tonight. If we look to the east, we see the summer triangle is getting really high in the sky now. The summer triangle, if I remove the lines, is the asterism formed by Deneb, Vega, and Altair, and each of them is part of its own constellation. So Deneb is part of a constellation called Cygnus. Right there, you see that's Cygnus the Swan. If I remove everything right here, the lines we would trace, we'd take Deneb out to Sauter, and then we could go one way to Epsilon Cygni, and then Zeta Cygni to the east, and then we could go from Sauter to Delta Cygni, Iota Cygni, and Kappa Cygni to the west, and those form the two wings of the Swan. And if we go from Sauter out to this always calls it Gaia DR2 whatever, but we all know this star is Albireo. Albireo is the beak, right? And those we got the long neck and the beak. See, to me, this looks more like a swan, right? That's a swan. That is Cygnus the Swan. Cygnus is host to a couple of really cool objects. Right here, Caldwell 20. This is also called the North America Nebula. This one's a challenge object. You got to get somewhere decently dark. I've actually had better luck making out the North America shape of it with binoculars than with a telescope, interestingly enough. I don't know why that might be. Something about when you concentrate the light a little bit, it can help if you're not going too high power. But this is a nebula that is vaguely in the shape of North America. We got Florida right there. I live about here. And then we've got the Gulf of Mexico is this nice dark patch. And then, oh, look, a Starlink satellite. And then we've got coming down here, going into Central America, right? And Canada's over here someplace fading off into space. An interesting fact about the dark patches in nebulae, by the way, while we're on the topic of a nebula. And in fact, to talk about this, I'm going to bring up my visuals. Why not? And I will stay on the topic of the North America Nebula. Let's stick with that. Here we go. Here's a picture that's going to put it nice and upright. Let me get that ready. Whoa. Okay, let me zoom out a little bit. This thing had me all the way in it, because I think when I was doing the James Webb images, I did that. I moved really close to one of them, and I didn't undo that since last time. Here it is. This is the North American Nebula. Again, you can see Florida. You can see this star almost perfectly marks Jacksonville, where I live. I want to find out what star that is. That's my star. But here we have the Gulf of Mexico, which is this sort of dark region here. And it's easy to think when you're looking at a nebula that anywhere you see that it's not, right, where it's not glowing, that surely that's where there's a gap in the gas cloud. But that's not actually true. Most of the time what you're seeing in the nebula when you see dark areas or missing pieces of the nebula is that this dark patch is actually made of the same stuff as the rest of the stuff you see glowing. What's happening is that the gas is being ionized on the inside of a three-dimensional cloud, right? So we look at this, we see a flat image of the United States and Central America and Canada and all that. But really what we're looking at is a sort of three-dimensional ball of gas where the interstellar medium, I talked about it earlier in the show. That should be the topic. Actually, we might just make this the nebula episode. But the interstellar medium is just sort of everywhere in the galaxy. When new star formation happens, the radiation pressure, the radiation from the stars will push back against the gas and cause an opening and will also ionize that gas. And so nebulae typically are these sort of bowl shapes. There's simply these gaps in the gas cloud where the gas back here is illuminated, and we can see that because what would be blocking our view has been blown open by that new star formation. But some of these areas, a bit of gas comes around and blocks the light and is silhouetted against the light, and that's actually what you're seeing with this dark region here. Another nebula that shows this really well is, of course, our old favorite, the Orion Nebula. Everybody loves the Orion Nebula. How could you not? This thing is cool. So we're going to pull this thing up here. So this image really shows, you can get the idea, right? And you can see the other side of the ball even, that this entire picture is actually full of gas, right? We just see the part where a hole is open in the side of it, and this bright area is where a handful of stars called the trapezium are lighting up and ionizing all of that gas. And we can easily see in this picture that these dark streaks, and this thing right here, which normally in a visual telescope is just black, is actually purple in this because this person took a long enough exposure to highlight that gas. And it makes it very clear that this is in fact gaseous material. This is not just a gap in the gas cloud. This is actually where something is coming around and blocking some of that nearby starlight. And here we can see along this edge and along here, almost looking like the lip of a bowl, right, where the light is illuminating it. I'm getting a buzz here. Let me see. I always like to check my phone during the show because some people will text me a question, but that's not this. This is some kind of scam. But anyway, so that's we can really see that in the Orion Nebula, and that's kind of what's happening with most nebulae that you look at. Let's see here. Charlie Mike, which is to say my dad, says, I read once that Deneb was incredibly bright but incredibly far away. Is that true, or is it another star that I'm thinking of? No, you're thinking of Deneb. That is absolutely correct. Let me, because now that we have a question, let's go with the question. I'm going to go back to Stellarium, and we're going to talk about Deneb real fast. So, star brightness is measured on a scale that we call magnitude. And it is an inverse scale, kind of like earring gauges, right? So, you know how, when you get your ear gauged, you start the lower numbers, and I think they go into negatives. I'm not sure. I don't obviously have that myself. Are actually thicker gauges, and then the smaller numbers are thinner, right? The magnitude scale works the same way. Brighter stars have a lower magnitude than dimmer stars. And the sun is given a magnitude that's negative, right? Because we measure apparent magnitude. That's how bright it looks from the Earth, right? So Deneb is a fairly bright star in the sky. And if we click on it, we see that it has a magnitude of 1.29, right? So that's a 1.29 magnitude. If we look at Altair has a magnitude of 0.82, so that's much brighter. First magnitude are some of the brightest stars. Anything that starts to get below first magnitude are some of the very brightest stars. I think I can pull it up actually. Sirius is the brightest star in the sky, and it's a bit more of a wintertime thing, but luckily the software also lets me just look clean through the Earth. So Sirius has a -1 magnitude, right? Just to give you an idea. The sun, magnitude -26, right? Where did the moon go? The moon, magnitude of the moon varies actually by phase, but I keep clicking all the things. This is saying -11.83, right? Okay, so this is the thing, and it's a logarithmic. Oh boy, I've broken it now. How do I get? There we go. It's a logarithmic scale as well. So each level is 10 times as much. So a magnitude 1 star is not twice as bright as a magnitude 2. It is 10 times as bright, right? So it's a logarithmic scale. So that should give you some idea of what a -26 means, right, for the sun. Okay, so Deneb is a 1.29 magnitude when observed from the Earth, and Altair is a 0.82. But look at this distance figure. Altair is only 17-ish light years from the Earth, right? The further away a star is, the dimmer it's going to appear from Earth because it's so far away. And by and large, when you look at the sky, it's easy to assume that the brightest stars are close. Vega, with its 0.09, is only 25 light years away. So it's further away than Altair, but much brighter. So that tells us that this star is, in reality, brighter, right? If you were next to it versus being next to Altair, the intrinsic brightness of this star is more than Altair. And so generally, a lot of the really bright stars in the night sky are within a couple of hundred light years. But Deneb is 1,400 light years away and still appears to have a magnitude of 1.29 when viewed from the Earth, which means that is an outrageously bright star, right? Sirius, that I mentioned before, where did Sirius go? Sirius, the -1, it's about, I've read different things. Some sources say 11, some say 8.6, according to Stellarium here. So somewhere around 10 light years away for the brightest star in the sky. And what that means is, although Sirius is the brightest when viewed from the Earth, if Deneb were as close as Sirius, it would absolutely blow it clean out of the water in terms of brightness. It's honestly fortunate for us that Deneb isn't closer than it is. In fact, I'm going to look up real fast, what is Deneb's intrinsic brightness? Deneb's intrinsic magnitude. For anyone here who's a fan of the show Community, anytime I start talking about magnitude, there's a part of me that wants to go pop, pop. All right, so let's see here. For everyone that doesn't watch Community, you're like, what was that joke? All right, I'm having a hard time finding that number, but let me keep looking real fast. I might just pull it up. You know what? Wikipedia is often good for this. They'll have a whole sidebar with all the astrometry is the word, with all the measurement stuff. All right, so let's see here. Luminosity. Okay, so it's not giving it to me in the magnitude scale, but this is going to achieve what I wanted to achieve anyway, because I was going to compare it to how many times brighter than the sun, and I'm glad that it does this math for me, because I didn't realize how big a number this was going to be. Deneb is 196,000 times brighter than the sun, plus or minus 32,000. It is 196,000 solar luminosity. That is absolutely unreal. Let's see here. Coop, it's cool. Enjoy the Discord. You don't have to. It's falling apart. You got to deal with it. All right, man. Deal with that, I guess. But Cooper, I never worry about your participation in the chat. Okay, so yeah, but Dad, to answer your question, yes, Deneb is an incredibly bright star that is just very, very far away, which is the only reason why it doesn't utterly dominate the night sky. Because again, if we orbited Deneb at the distance that we orbit the sun, it would be 196,000 times brighter. That's like blind you through your closed eyelids bright. that is probably just vaporize you. I honestly don't even think you could be near it, because with that brightness is coming heat and radiation as well. But nonetheless, Deneb is a nice treat of the summer sky, and we have Vega as well in Altair. A couple of objects in this piece of sky that I really like, again, continuing with the nebula theme, is the Ring Nebula. Is a really nice one over here, halfway between Sheliak and Sulafat. I like to give fun facts about these stars. Sheliak, so Star Trek and its imitation show, The Orville, both like to use real stars in their episodes. And there's an episode of The Orville that takes place on a planet orbiting Sheliak. It is not an eclipsing binary in that episode of the show, but there is actually an episode where they go to Sheliak. And so I think I'm trying to remember which one it is, because I was thinking it was the one about the planet that's obsessed with astrology, but actually that's Gamma Geminorum, actually, which is another real star. And they call the people on that planet the Regorians, and that really is. Regor is another name for that star. But I'm getting off topic now. So anyway, between Sheliak and that other one is the Ring Nebula. Also, it's showing up really nicely. If you find Albireo and you go a bit to the right, do you guys see this grouping of stars? This is an asterism that is called, I forget its designation. It's something 377. I'm blanking right now. But we also call it the coat hanger because there's the hook and there's the line. This one's really cool in a pair of binoculars. A telescope will sometimes zoom in so much it's hard to see the coat hanger. But through a pair of binoculars, this coat hanger asterism is really cool. It's a fun one to show kids at like outreach events too, because you point the telescope and you're like, look, it's a coat hanger, right? Even when I zoom out, it's really, man, look, it's right there. It's a nice big one. But speaking of nebulae in this piece of sky, if we take Solder and Epsilon Cygni and Albireo, and then we imagine where we would put a fourth star if we wanted to make a rectangle, you'll see it highlighted it because there's a thing there. This is Messier 27, also known as the Dumbbell Nebula. Okay. We're at about the 8:30 mark, which means we have an hour left in the live stream, and I've been talking for a bit about what's in the sky, which I'm always happy to do. But I'm just going to check the chat and see if we have any questions. And we dropped down to 2 viewers. Man, I hope we're not having technical difficulty and having people drop off due to technical reasons. I always do like to say that you can always jump in at any point in the show and hop off at any point in the show. You don't have to stay here for the whole 2 hours, obviously. But let's do this. Let's talk about nebulae. Why not? That seems to be the topic, and no one's giving me a topic in the chat, which is fine. You guys, if you're enjoying the show, enjoy it how you enjoy it. If you just like to sit here and listen to me talk, but I'm going to keep going with the topic of nebulae. So the word nebula, first of all, comes from a Latin root that basically just means cloud. And the history of nebulae is that in the early days of astronomy, astronomers knew about the stars, right? They knew about the planets, and they knew about comets, but they kept finding these blurry things, right? They would literally point the telescope at a piece of sky, and there was something kind of blurry, right? So they named it nebula, meaning like cloud, right? Even the word nebulous in our modern day English language means vague, right? These objects were vague. They were blurry things, and nobody really knew what they were. And it used to be that the term nebula was a catch-all for any blurry object, including many that nowadays we would not consider to be proper nebulae. It wasn't until later on that we started to learn what these objects were. If you were here for my Galaxy special, you remember me talking about this and how there were these spiral nebulae that turned out to be other galaxies. We figured out that those were other galaxies, and the term galaxy was coined to refer to that class of object. And as these objects became more defined as what we call them, the term nebula now refers specifically to clouds of gas, or dust, which dust is a sort of vague term in astronomical terms. It basically is just, it's not like dust like you'd wipe off your table. When we talk about dust in the universe, we're talking about clouds of more complex material than just hydrogen, right? Things like organic compounds, that kind of thing. But that's what nebulae are. They're basically just clouds of gas. And you might think that our galaxy has these distinct nebulae, these little pockets. But actually, there's something called the interstellar medium, which is the fact that between the stars, interstellar, is this sort of very, very tenuous gas and dust. It's more concentrated in some parts, less concentrated in others, but it's sort of everywhere in the galaxy. And it is very, very, very thin. A common misconception about nebulae also applies to the interstellar medium, which is that we assume that these are thick clouds, right? Like if you look at pictures of them, they certainly can look that way, right? Let me pull up my visuals here. There we go. So, if we look at something like this, or if we look at like the, let's do the Eagle Nebula. All right. So we see the Eagle Nebula right here, or even especially if we zoom in on a piece of the Eagle Nebula, like these look like thick clouds, don't they? This almost looks like thick smoke or something. Like you imagine you would choke in this cloud. It's so thick. But the reality is Nebulae are just barely more concentrated than hard vacuum, right? Hard vacuum would be the absolute absence of any matter. Um, but the reality is the vacuum of space is not an absolute pure vacuum. You get in a unit volume, you might get an atom or a couple of atoms or whatever. For I forget what unit volume. It's very very little though, very small amount of material. The interstellar medium is thicker than that. There's a bit more going on there, but not by a lot. And I always tell people, if you had this piece of the Eagle Nebula here, right, if this were pure oxygen and you put somebody inside it, they would suffocate, right? It is absolutely tenuous. If you were inside of a nebula, you wouldn't see it, right? In fact, we had to be away from a nebula to see the light, the very faint aggregate glow of this ionized material concentrated from our perspective makes it visible. I've wondered what would it be like to be inside of a nebula, and actually the reality is you probably wouldn't tell, right? It would contribute a very tiny amount to the ambient sky glow of your sky when you look up, and would prevent you from seeing some of the more distant stars. And in fact, we are in a way inside of a nebula. There is a bubble in the interstellar medium, and we are kind of like near the edge of that bubble. So look up at the night sky. That's kind of what it would look like to be inside one of these, maybe a little bit more concentrated. What we see as nebulae that we can see in our telescopes is when something is illuminating that tenuous material or is providing illumination behind it so that we can either see it glowing or silhouetted in some way. And that allows us to observe these nebulae. Here's a... got a question. Oh, we got several questions in the chat. Okay, cool. What do I think of Venus being such a good option of terraforming, but yet so impossible? I don't know if I would consider Venus a good option for terraforming. Venus is a bit of a hell world. So the problem is Venus is what you get if you have a greenhouse gas effect taken to the absolute extreme. Bear in mind, no matter how badly we treat the Earth, it will never be Venus. But Venus has a thick atmosphere of carbon dioxide, and that carbon dioxide traps heat from the sun to the point where it's like 900 degrees in the shade on Venus. You can melt lead in the open on Venus. So that's why it's really not viable. That and the enormous pressure, because that carbon dioxide, is heavier than oxygen. It makes it super high pressure as well. Any probe we've sent to Venus to image it from the surface basically snapped a bunch of images, beamed them, and then just got destroyed. So Venus is like, if I had to imagine that hell were a physical place in the universe, it would be the surface of Venus. Got another question here. Some famous space pictures, parts are blacked out and censored. So that's an interesting question. There's obviously, you could get into like a conspiratorial mindset about censorship going on with some of these images, but the reality is these are actually quirks of how the telescope works. So a lot of Hubble images will have this stepping stair shape. And this is because of the way Hubble's sensors were arranged, that you basically have one sensor took this picture, one sensor took this picture, another one took a picture down here, and then another one would take a smaller image, and those images would be stitched together into a bigger picture. So what you're actually seeing here is not one image, but is actually a collage. And if we zoom in, you can even sort of see the seams, right, where one image is butted up against the other. So these black areas that you see in the Hubble out here are not actually censorship as such. No one has intentionally blacked that out. That's actually just a lack of an image. There was no sensor taking a picture there. So a lot of Hubble images have this general shape to them. That's a common thing. It's a sort of a fingerprint of the Hubble, just like how the James Webb fingerprint is that neat little spiky pattern, which you see that the Hubble has as well. But the James Webb is distinctly the 6 spikes, or the 6 big spikes and the 2 small spikes. The 8 big spikes and then the little ones in between. That's the James Webb layout. But also, if I pull up an image, here's what I'm going to do. Markarian's chain is a good example. So I bring up Markarian's chain. We find some pictures. It won't be long until we find this guy, right? This is a picture of Markarian's chain. And you'll see all these little black circles. So what's going on here? Well, what's going on here is that this image has been edited to block out stars in our own galaxy. So that you know, when you're looking at this image, that literally every speck in this picture is a galaxy, right? Markarian's chain is, of course, very obvious here, but all these other specks are all galaxies. So this is just the choice of the person who made this image to block out nearby stars so that they are not distracting from the subject matter of the image. So hopefully that answers your question a bit. If I had some other specific examples of images that have blackouts and things in them, I could address those as well. But I will move on because we did have a really good question about open star clusters and nebulae. I'm going to pin that real fast and see what other questions we have because I want to dive really deep into that one. Tom says, what are the different types of nebulae and how can you tell the difference? That's another excellent question that actually relates really well to Ryan's, so I'm going to come back to those as well. And then wasted potential. Cool. Hubble poster thinking it was all right. Cool. So let's get back to the question then. So let's talk about the different kinds of nebulae, and as I discuss them, it's going to naturally lead into the question about star clusters because the relationship between star clusters and nebulae is undeniable, right? Also, you say open and closed star clusters. Actually, the two types of star clusters are open and globular. Open stars are more loosely associated. Globular, they form a tight ball of stars. I could show an example of one of those. Just back up real fast. And do globular cluster. Okay. So this is what a globular cluster looks like. It's just a tightly packed ball of stars. This picture, I think, does a better job because you can see what it looks like against the background field, this hyper concentration. But yeah, let's talk about the different kinds of nebulae. So there's a few different ways to classify nebulae. There are three broad categories of nebulae, and then so there's some subcategories. So the three broad categories are dark nebulae, reflection nebulae, and emission nebulae. So we'll talk about dark nebulae first, because it's a very broad kind of category. Just about any old kind of nebula can produce dark nebulosity. To give an example of this, I'm going to show the Coalsack. Oh, right. I should be more specific. Coalsack Nebula. I'm just acting like, oh boy, we don't have a lot of good results for Coalsack. Let's try... What's another good dark nebula? B23 Nebula. I know a lot of them have B in the indication. Okay, cool. So this is... And this is actually an infrared image here, not visible spectrum, but still shows the idea. You see these dark smudges, right? These are called dark nebulosity. Now, dark nebulae are not compositionally any different from the other kinds of nebulae. The difference comes in the fact that they are not glowing in any way. And in fact, they are blocking the starlight behind them. And so they're silhouetted. So just like if we turn off the lights in the room and shine a light behind my head, I would be a black shadow of a person because I'm silhouetted by that light. So the dark nebulosity that we see is a silhouette nebula, right? It's a place where the starlight is just illuminating it from behind. The other two kinds of nebulae are sometimes grouped together by the term bright nebulae. And the term bright nebula can be a little misleading because some of them are very faint. But what we mean by bright nebula is that it's emitting light, right? So let's talk about the different kinds of bright nebulae. So the two types of bright nebulae are what we call emission nebulae and reflection nebulae. So an emission nebula, and a good example would be the Orion Nebula. So what's happening in an emission nebula is that stars, nearby stars, are irradiating that material and causing it to become ionized, right? Where the electrons are stripped from the atoms and they gain a charge, kind of like what happens in a neon light. You run a charge through an ionized gas and it glows, right? So the ionization of this gas makes it glow, and that glow is what we see, right? So this tenuous material is not just illuminated, but it actually is glowing. It's emitting its own light. So these stars in the middle irradiate the gas, and then the gas glows. Some emission nebulae are actively being irradiated by something and ionized by a nearby star or something. But there's another class of emission nebulae that I'll get to in a bit that are ionized because of some traumatic event that gave them a bunch of energy, and that ionization will fade over time. It will slowly fade. Reflection nebulae are some of the hardest to observe. I'll just say right now, if you're looking through a telescope and you look at your chart and it says this is a reflection nebula, get ready for a hard time, because reflection nebulae are often extremely faint. But I'll give an example of a reflection nebula, and that is the nebulosity that surrounds the star of the Pleiades, the stars of the Pleiades. So in this image of the Pleiades, this gas is not being ionized by these stars. What's happening is the stars in the Pleiades are lighting up some of the tenuous interstellar material because of how bright they are, and this light is just reflecting off of this gas and dust. And I want to say that the stuff in the Pleiades is what we would call dust in the astronomical sense. So, and I need to do more research on dust, because I don't fully understand myself what is meant by dust in astronomy, and I feel like I'd like to have a better understanding of it. But the Pleiades stars are illuminating this gas cloud. And what's interesting is this gas cloud is actually not associated with the Pleiades. This is a chance alignment. The Pleiades are moving through the Milky Way, and for right now, they happen to have collided with this cloud of gas and lit it up, right? So we can see it. So that is an example of an emission nebula. Gonna take a quick look at the chat real fast. The glowing gas is cool, man. I gotta agree with you on that. Like I said, I would call myself a bit of a nebula nerd, man. I think nebulae are cool. I really do. I could definitely talk about them. So let's talk about some of the different types of bright nebulae, some of the different types of emission nebulae and reflection nebulae. A very common type is what we call a molecular cloud. I keep showing the Orion Nebula. Let me give some other examples of molecular clouds. We're going to go to another one of my favorites, Eta Carina. Right, the Eta Carina Nebula. This nebula is nuts. This thing is actually bigger than the Orion Nebula and brighter. It's just not visible from the northern hemisphere unless you get somewhere very close to the equator. I've observed it myself through a telescope down in the Florida Keys. It was down near the horizon. I was looking out over the ocean and was able to spot it. But normally it's considered a southern hemisphere object, and I feel like the only reason this thing isn't as popular as the Orion Nebula is just northern hemisphere bias, because this thing eats the Orion Nebula for lunch. But to talk about what it is, it's what we call a molecular cloud. And what that is it's a cloud of molecular hydrogen. So we talk about molecular hydrogen. Hydrogen is one of the elements on the periodic table. It's the simplest one. It's just one proton, sometimes with one or two neutrons in the case of tritium and deuterium and tritium, respectively. But it may have an electron orbiting it, or if you ionize it, that electron just goes away, right? And you just get a proton, basically. But if it is an atomic form, or it does have an electron orbiting around it, two hydrogens can bond together to form H2, right? Which is the molecule hydrogen. That's the way hydrogen exists if I had like a container of hydrogen gas, right? So that is what comprises a molecular cloud. That's why we call them molecular clouds. That's why these are also sometimes called H2 regions, right? Now, what's really cool about molecular clouds is that hydrogen is star fuel, right? You get stars, what they do is they turn hydrogen into heavier elements. That's the fusion process that powers a star. Again, another thing I really like, you see these strips of the thing, and now you know what these are, right? This is intervening gas. This, again, is a three-dimensional object that we're looking through that's kind of blown out over here and blown out over here, but there's some material in the middle here blocking that light. But yeah, so this is all molecular hydrogen. And what happens in these molecular hydrogen clouds is normally they're not glowing, right? So there's a lot of this molecular hydrogen in the interstellar medium that we just don't ever see, right? So for example, over here, right, there's some over here, you just don't see it. It's just not glowing. But if if clumps can form in this gas cloud, where there's regions that have a higher density than the region around them, that more dense region of this cloud will exude a gravitational force on all the gas around it, which will pull it into itself, and so on, and will form an ever growing sphere of gas. And when you have enough hydrogen gas in a big ball like that, its own weight, its own gravitational pull is going to crush it in so hard that it starts to heat up. And if you get enough material, it gets hot enough that fusion starts going and it clicks on and becomes a star. Right, now you've got fusion. This is how stars are born. They're born in H2 regions like this. And this is finally going to get me back to Rudy's question. Rudy, if you're still with me, I appreciate your patience. Or not Rudy, sorry, your last name is Ryan. I appreciate your patience, Ryan, if you're still with me, because this is the answer to your question. Are open clusters a form of nebula? Back in the day, they would have been called nebulae because they were blurry, but open clusters are the result of nebulae. H2 regions become open star clusters because what ends up happening is all of this material starts turning into stars, right? I can show you another example that's further along in this process, and that's the Rosette Nebula. Also, there's a bit of a pattern that's going to emerge as we look at pictures of these. I want to see if you guys spot it. I'm just going to wait to see if anyone points something out in the chat of a pattern that you notice when it comes to these H2 regions. I'm just curious. Here we see the Rosette Nebula. We see this gas all around it, but we see all these stars, this little cluster here in the middle, right? These stars have formed out of this gas. And what I forgot to mention, so normally they're not glowing. Once star formation does start to occur in an H2 region, the radiation coming off of those stars will ionize the gas and turn it into a form of emission nebula. Right? So that's what's happening here. That's why we can see the gas as it's all ionized and it's glowing. And if I zoom out of the picture, that's a little bit clearer. You can see there's the nebulosity all around. You can see the opening in the middle. You can see this gas is starting to get dissipated a bit and has formed a nice little cluster of stars. If I pull up the Lagoon Nebula, which I mentioned before, the Lagoon Nebula is a cool one. Wait till you guys see it. This guy is real cool. Here's a good picture of it right here. Bring that up. Let that load for a second. Here we see this bright patch is because there's a lot of stars in there, but you see how they're kind of fuzzy. There's a lot of gas around them. But you see there's a nice little cluster over here as well, right? Forming in this one right here. That Pleiades I showed earlier was born from a nebula, but that nebula is long since gone, right? The Orion Nebula is kind of the same way. Let's see, what other nebula can I show? That's a good example. We'll do the Eagle Nebula real fast. The Eagle Nebula has the famous pillars of creation. Here's another picture of it right here. And the Eagle Nebula, I think, also does a really good job of showing the premise of what I'm talking about. And actually, the Eagle Nebula is a really good example because it shows a couple different phases of this process. You can see a couple different stages of the process. So here we have, again, the eagle head of the Eagle Nebula is just some of that gas wrapping around. Really cool looking. We can see this nice cluster of stars inside. A lot of star formation has happened already in the Eagle Nebula. But you can also see, if I click to zoom in real fast, and I can already tell it's going to take a second for it to register the zoom. This is a big old picture. Oh my goodness. You see these little nodules, these little knots, these little things forming. These little clumps, right? Little globs, right? Even in the background, you see this big sheet-looking thing, but you see this little nubby on the end of it, right? Those are areas where the gas is more dense than what's around it. So those are places where stars are probably about to form, right? Hopefully, if there's enough material, we'll get a star out of that, right? Some of these, they don't gather enough, and we get what we call a brown dwarf, which is basically just like Jupiter on steroids. It's like a huge gas giant, but not enough to become a star, right? And sometimes you get a really cold, by star standards, a cool red dim star called a red dwarf. And those things last forever, by the way. They're going to be here long after the universe is gone, or most of the stars of the universe are gone. But we don't usually see a lot of those. They're hard to see. What we're looking for is bigger clumps that are going to form bigger, brighter, bluer stars, like some of the ones we see in the nebulosity here. So I'm going to check the chat. Has anyone noticed the trend so far? Planetary nebulae. Yep, I'm definitely getting there. I know I'm spending a lot of time on the H2 regions. I am going to talk about all the other types of nebulae, though, because I really do want to make this a nice, comprehensive nebula episode. Has anyone noticed a pattern with the nebulae that I've been showing so far, these H2 regions? Anyone noticed anything about them? Something that they have in common, besides the star clusters? I'm curious. I'll give you guys some time to mull that over. But I'm going to go ahead and move on now and talk about planetary nebulae. So first of all, the term planetary nebula is dumb. It's a dumb term. I hate it. It is the worst term. It's a misnomer because planetary nebulae have nothing at all to do with planets. Planets are just not involved in any way with the objects that we call planetary nebulae. It's a dumb name. Here's where the name comes from. William Herschel observed one and said, it kind of looks like a tiny blurry version of the planet Uranus. Or maybe it was Neptune, I forget which one. And the name stuck. And so we're stuck with it. But what a planetary nebula actually is really cool. Let me bring one up. Ring Nebula. I mentioned the Ring Nebula earlier tonight. Let's take a look at what it would look like through a really cool telescope. So this is the Ring Nebula. Some Arabic writing, that's kind of interesting. All right, here's the Ring Nebula. And what this is, a planetary nebula is one of the ways a star can meet its end. There's a couple different ways a star can die. And one of the ways a star can die is to become a planetary nebula. To do that, a star has to be a sort of middle-sized star. Our own sun is the right size to do this. Bigger stars are going to become a different type of nebula that I'll show you here in a second. But stars about the size of the sun become a planetary nebula. Now, it's almost a little weird to call these different kinds of objects nebulae because really there's entirely different mechanisms responsible for their existence. But we call any cloud of gas a nebula, and this is a cloud of gas, so we call it a nebula. So what happens is you get a star about the size of the sun, and it runs out of hydrogen fuel in the core. When that happens, the core starts to collapse because the radiation pressure of the fusion reaction is what's preventing a star from imploding on itself, right? Every star is trying to explode and implode at the same time all the time. So when that fusion reaction runs out, the star begins to collapse. The core collapses faster than the outside because stars are so big, they don't actually collapse in one solid unit. The inside collapses, and then there's like a propagating wave of collapse. So the core will collapse long before the outer layers of the star even know something is happening. No, as if they have consciousness, but before they even register that anything is happening inside the star, the core has already begun a core collapse. And what actually happens is that core collapsing heats up the material because as it collapses, it heats up, generates more friction, and that heat actually allows it to get hot enough to undergo fusion of the helium in the core into even heavier elements. And now that creates a pressure of radiation which halts that core collapse, and that wave of radiation pressure propagates back out to the outer layers of the star. And so that sudden amount of extra energy from the core makes the outer layers swell up. As they swell, they cool, because the ideal gas law says that as gas expands, it cools. Even though stars are technically plasma, they still obey the law. And they turn red. And this is where we get a red giant. Well, this process of collapse, fusion, expansion happens over and over again. So you can imagine that the star is like pulsing from within of pushing out the outer layers. And it pushes the outer layers, it pushes them again, and it pushes them again. And eventually it just blows away all the outer layers of the star. Just blows them off. The star can no longer hold on to that material. It swells so big that that outer layer is actually further away than a orbit around that star of that material would be possible. It's so far away that the star's gravity can no longer hold it, and it just starts drifting away, right? And so what you get is a roughly spherical, expanding cloud of ionized hot gas with a tiny chunk in the middle of carbon. Usually carbon, maybe some oxygen in there. That is still glowing just because it's so hot, but is no longer capable of fusion. You get the core, and you get the expanding cloud of gas. That is what we call a planetary nebula. And in this picture, you can actually see it right there. That's the core. And then this is all the outer layers. This whole thing was one star that died and went and just blew away the outer layers. Just sort of puffed up its cheeks and blew its own body out to the stars, right? And this material is an example of what I was saying before. This is not being ionized by nearby stars. It's ionized because it was a star. But this will all cool and stop glowing eventually. And what will be left is just that white dwarf. That's what we call that. That white dwarf core will be the only thing left that's glowing. And white dwarves glow not from fusion. That's a dead star. It's not still doing fusion, but just from leftover heat. And they're so hot, and it takes so long for radiative heat loss to cool them down, that the universe isn't old enough yet for any of the white dwarfs to have cooled down. So there are no... Eventually what will happen is it'll become a black dwarf. It just runs out of energy and no longer radiates. It no longer glows at all. But the universe is not old enough for that to have happened yet. So we don't have any black dwarfs in the universe. And the white dwarfs actually are going to last a really long time. They last a good while because radiative heat loss is not very efficient, right? So that is what a planetary nebula is. There's one more kind of nebula I want to talk about, and that is what we call a supernova remnant. And for that, I'm going to show you guys the Crab Nebula. Crab Nebula is sort of everyone's go-to example of a supernova remnant. If you guys want to, we can look at some other ones, though. They are really neat objects, these supernova remnants, if I'm being honest. Let's bring this guy up real fast and take a look. I'm waiting for it to load. Maybe I didn't click it. Okay. Thought I clicked it and it was just taking a while. Okay, here we go. Look how shredded this one is. You see how this is a whole different beast than what we were looking at, right? So the really big stars, what they do is they do that same process of contract, expand, right? And every time that core collapses and does another kind of fusion, a more powerful kind of fusion, it gets hotter and is hot enough to generate fusion as a shell around it. And so big stars become like onions where they have layers, where there's like this outer part that's doing hydrogen fusion into helium, and then you got helium into carbon, oxygen, nitrogen. You got all these different things all the way down. A good chunk of the star, though, is still just hydrogen. In fact, the interesting thing is, with the planetary nebula as well, most of the material in a star, most of the hydrogen goes unused, right? The star uses up what's in the middle of it, where fusion can happen, and then dies. And then there's still a ton of fuel left over, which is why we can get more stars that form out of that, and this material actually gets recycled a bit. But getting back to this, these big stars, they'll do that. They'll have those onion layers inside, and they don't just blow the outer layers out into space. They're heavy enough that that doesn't happen. There's enough gravity there to hold on to it. But what eventually happens is that the star will make iron in the core, right? It'll fuse together whatever it fuses to make iron, and I don't understand the fusion process 100%. I don't know the exact reaction that produces iron, but there's a fusion reaction that results in iron, and the iron reaction is actually energetically negative. It's a loss. So all of these fusion reactions, you have to put some energy in to get it to happen, right? That's the energy of activation that's required to get that reaction to occur, right? You have to overcome that. That's why stars don't just start off making iron. But the reaction that produces iron gives off less energy than is required to make the iron, right? That energy gets stored in the iron itself. It's in the form of the bonds and that kind of thing in the iron, but it's a loss for the star. So the core is now undergoing this type of fusion where it's losing energy, right? It's losing money on every exchange. And this loss of energy, it results in the radiation pressure that normally keeps a star from imploding. That's gone now. And that collapse that causes the fusion to heat up again and make us do another cycle, that's not going to happen, right? Because the problem with iron. So now the core collapse is irreversible. It's going to happen. There's nothing we can do to keep this star from imploding. But as the whole mass of that whole star, and really, again, the outer layers are kind of staying put. It's the core that's doing this. The inner layers are doing this. Collapses super hard, and it produces a lot of energy all at once, and it fuses that iron into much, much heavier stuff. It jumps way up the periodic table. We get things like uranium from this. And it does it all at once, real fast, produces an absolute ton of energy. And if we know anything about what happens when you produce a whole bunch of energy all at once, that's an explosion. So the star makes iron, implodes, and then boom, it just detonates and just explodes itself and just spews its guts all over the universe. And this is actually the source of things like iron, like potassium, right? A lot of the stuff that we're made of only exists because of the violent deaths of really massive stars. The iron in your blood was made this way, right? There is no other natural process that makes iron. It's made like this. And this supernova remnant is donating all of these new heavy elements back into the universe. And when new stars form out of this gas cloud, the interstellar medium, that interstellar medium is now seeded with these heavier elements. And so second and third generation stars will have clouds around them of the stuff that's not useful for making a star. And that's where you get things like planets. But this type of nebula is called a supernova remnant. Now, what you get in the heart of a supernova remnant is one of two things. You get a neutron star, or you get a black hole. And that depends on how big this star was before it detonated. So, big stars form neutron stars, and then really big stars form black holes. Now, what a neutron star is and what a black hole is are kind of difficult to explain. I might circle back to it, but I want to stay on the topic of nebulae for just a second longer. But that's a supernova remnant. That's really the last type of nebula to discuss. So to reiterate, we've got dark nebulosity, which is just any nebula with something illuminating it from behind. We have emission nebulae, or we have bright nebulae, which are any nebulae that are glowing or emitting light, and those are broken down into reflection nebulae, which is just gas that's lit up by a passing star, and emission nebulae. And then emission nebulae are broken down into H2 regions, also called molecular clouds. Charlie Mike posted something and then retracted it. Okay, he's gone, I guess. I guess he changed his mind. Imagine living on a black dwarf. Yeah, that'd be interesting. FYI, the center star in the Ring Nebula is a double star. The image of JSW. That's right. Tom pointed out the James Webb Space Telescope image of the Ring Nebula actually shows that the star at the center is a binary pair. There's another star in there with it. How wild is that? Imagine taking a black hole explosion, take the uranium from that, and use it to make a mini supernova. Yeah. Right, by making an atom bomb. Exactly, right? You release more of that destructive power. So, anyway, so the emission nebulae, you get the molecular clouds, the H2 regions, and then you get the two kinds of star death, right? You get a supernova remnant in the case of a supernova explosion, or a planetary nebula, which is the dumbest name ever, in the case of medium-ish sized stars when they expire. Now, I'm going to circle back around. When I was showing the pictures of those molecular clouds, those H2 regions, nobody has pointed out in the chat yet what the pattern was, that I was curious if you guys would notice it. So I'm going to bring it back up again. Let's do Etta Karina. Again, I want to remind everybody that's watching right now, if you are in the chat, say hi. Definitely everybody is welcome to participate in that chat. I love hearing from everybody. And I'm always curious. One time I did this show and someone said hi from the UK. And I was like, somebody in the UK is watching this show. That is cool, man. So it lets me know that the show is getting to people. And I like to hear all about it. So, all right. So this is our Eta Carina Nebula. This is a really big picture. So the thing I was wondering if you guys would notice is that the pictures I was choosing to show you of the molecular clouds, they're all pink, right? They're pinkish purplish. Did anyone notice that? Right? Eta Carinae is nice and pink, right? If I pull up the Eagle Nebula. Now, not all the pictures, and I'm going to talk about why not all the pictures show this, but the pictures I'm choosing to select, and I'm choosing them for a reason, they look pink, right? So, Eagle Nebula, pink. Lagoon Nebula. Right? Nice and pink. That's because that's the color of ionized hydrogen. It just looks pink like that. when you see images of H2 regions, molecular clouds, that are not pink, it's usually because some form of filter has been applied, or we're looking at a different part of the spectrum. So like this image of the Lagoon Nebula looks blue, but we're actually looking at it in the infrared in this picture, right? Or sometimes you're looking at a radio image, or sometimes you're looking at what we call a false color image. Like I'll bring up the Eagle Nebula again and show you. And what a false color image is, it sounds like we're being lied to. That's not what it is. It's just that these are not the real colors. What they did with this is this image is actually a bunch of images, right, stacked together. That's how we do astrophotography. But these images were taken with different filters that were filtering for very specific parts of the spectrum associated with particular chemical elements. And rather than just show them all the color they really are, which this whole image would just look like various shades of pink, NASA took those exposures from those different filters and assigns them a color. So one filter is green for this particular chemical compound, one is red or orange, one is whatever. And so that creates an image that is not the real color, but does convey visually the composition of the gas cloud, right? And so this image has a scientific value by showing us what the clouds are made out of, even though they're not really these colors. That Ring Nebula image I showed you earlier is also, if I'm not mistaken, a false color image. Because, again, these are colors resulting from saying, okay, we're going to dye, I think the oxygen is blue, and then I think the hydrogen, they make it red or whatever. So you can see the composition of the nebula. But when you're not looking at a false color image, the H2 regions are pink, right? The molecular clouds are pink. You notice I keep flipping back and forth between those two terms. Those are two words for the same thing. Why is that important? Well, when we look at galaxies like Messier 83, in the visual part of the spectrum, not applying false color, not applying special filters, we can look for pink. And that tells us these are H2 regions. All these little pink nodules you see here in M83, those are molecular clouds. And more importantly, they're molecular clouds that are being ionized by new star formation. So one of the things astronomers look for in images of galaxies is pink. If we see a lot of pink, that tells us that there's a lot of new star formation going on in that galaxy, because those are hydrogen regions that are forming stars and causing them to light up pink. So that was the thing. I was wondering if you guys would notice that all those H2 clouds were pink. Another thing we can look for while I'm on the topic is you'll notice all the blue. Different stars live different amounts of time. I guess I touched on stellar evolution a little bit. I can keep talking about it if you guys are curious. So different stars, I mentioned how they use up the hydrogen fuel. The bigger and more massive a star is, the hotter it burns. And so the more quickly it goes through, and burn is an inaccurate term, it's a nuclear fusion reaction, but even astronomers will talk about hydrogen burning when they really mean fusion. But the bigger a star is, the heavier it is, the hotter it is internally because of that mass. And so it burns through its fuel more quickly than smaller, cooler stars. And hotter stars are bluer than cooler stars. So when you see blue stars, those are big, hot, enormous stars. Stars like Deneb that we mentioned earlier that are burning through their fuel very quickly. And stars that are more towards the yellowish or reddish end of the spectrum are smaller stars that are burning through their fuel more slowly. They're not burning as hotly, right? It's still hot. I mean, the sun is obviously hot. But in terms of how hot stars are, it's actually a little bit toward the lower end. So why is that important? Well, it's important because the big, huge, hot blue stars are like rock stars. They live fast and die young, right? They don't make it very long. They last a few million years, not a few hundred, a few million years, and then pop. So if a galaxy is not replenishing its population of big, hot blue stars, we would expect that they all die, and then the other stars, because they last longer, are left behind. So galaxies that are not undergoing new star formation, that are older galaxies, should be more yellowish, right, than galaxies that are undergoing a lot of active star formation, where they are replenishing the supply of those hot blue stars. So you'll often hear astronomers talk about like young hot blue stars or whatever. It's because they don't last very long, right? So this galaxy, we look at the pink, we can tell there's new star formation because of the pink, but the blue also tells us that this is a fairly young galaxy. If you see a galaxy that has a lot of blue but not a lot of pink, which I want to say the Pinwheel galaxy or the Whirlpool, not the Whirlpool. I'm blanking on it, but it's Messier 33, the Triangulum galaxy. This guy. Well, actually, there's a bit of pink in there, right? Not nearly as much as we saw in M83, though, but there's definitely some pink. But sometimes you'll get these blue guys. I'm trying to see if I can find an example of one that's just blue. You know what? I think there's a good example that's part of Stefan's quintet. Let's take a look. No, I can already tell there's pink in there. Well, anyway, if you see a blue galaxy, the more pink that there is, the more star formation. If there's less pink, there's not as much star formation, but the fact that it's blue still gives a hint to its age. But if we take a look at some of the elliptical galaxies, like Messier 85, I think. And 87 is a good example. Yeah. M87, where they took that picture of the black hole, by the way. This picture, and this jet, that's the black hole, by the way. That black hole spewing that out. Isn't that cool? But you see this amber glow, right? Almost like an old-fashioned halogen light at night. That amber is because all the blue stars that used to live in this galaxy, long since gone, right? And the fact that ellipticals tend not to be blue, or pink, by the way, there's no pink in here, tells us that there's not active star formation going on in this galaxy, right? That's done. The galaxy's done making new stars. So this is an older, more mature galaxy that's burned through its supply of gas and is now this big elliptical galaxy. Elliptical galaxies are also thought to be the result of mergers between galaxies. And a lot of times in a merger, those gas clouds will hit each other. You might remember earlier when I was talking about the H2 regions that I said if something causes a density increase, right, for part of it to be more dense than the other part, that causes star formation. So that can happen when galaxies collide. And actually, I've got a really good example of... Give me a second to... Because I've got a really good analogy for this that occurred to me recently. Cluster, this is the game. Okay, there's a board game called Cluster that I had the joy of playing, and being the giant nerd I am, my first thought immediately was, this is like star formation, right? So, in Cluster, this is not an ad for this board game. They don't sponsor me at all. But in this game, you have this little rope on the table, and you have these magnets, and you're trying to add magnets to the area, but if they click together, you have to pick them up, right? And you're trying to get rid of all your magnets. So you want to try and space them out so they don't clump together. This is a really good analogy for what happens in an H2 region. So for most of the time, it's like this game, right? These magnets are all more or less evenly distributed, and their magnetic attraction is evening out throughout here. The magnetic field throughout this game is all sort of evening out, right? So if we take this magnet in the middle, this guy over here, and this guy over here, and this one, none of them is pulling more strongly than the others, right? And it's the same way with the little atoms, little molecules of hydrogen in a molecular cloud are all usually evenly distributed, right? So there's no reason for them to form clumps. There's no directionality to the gravitational attraction of these atoms. Because yes, even individual molecules actually do have gravity. It's just very, very, very minute. So the cloud is just sort of evenly tugging itself in every possible direction and nothing happens. But when you're playing this game, eventually someone's going to put down a magnet and another magnet will stick to it. And then suddenly, boom, a whole bunch of magnets will all grab onto that one. And they go, and they have to pick them all up, right? That's kind of like what happens with these molecular clouds, is if something pushes on the gas, then there's areas that are more dense than other areas, and now star formation can happen. And those overdensities can pull more material into themselves to become even more dense, and it's a chain reaction, and it builds. So why am I talking about this now? Well, I mentioned galaxy mergers. So when galaxies collide, that can happen. Those gas clouds will hit each other, create regions of increased density, Boom, star formation. Another thing that can happen is if a supernova goes off, the shock wave from the supernova will hit the gas cloud and cause that. In fact, Orion Molecular Cloud Complex. Now we know why, by the way, we know why the Orion Molecular Cloud Complex is called that. We know what a molecular cloud is. If we look at the Orion Molecular Cloud Complex, this is all the gaseous stuff going on in the constellation Orion. This is where the Orion Nebula is. We know there's star formation happening here. There's a couple other regions in here where star formation is happening. But look at this. Look at this big arc right here. This is called Bernard's Loop. What is this? Well, this is the evidence of a supernova that went off somewhere around here, and the shock wave of that supernova ripped through the Orion Molecular Cloud Complex and initiated star formation. So some stars, when they die, their death causes the birth of other stars. How crazy is that? So that's another fun thing we can learn about nebulae, is that something has to push on the gas, right? So supernovae can do that, but so can galaxy mergers. And this is another reason why the ellipticals are lacking in the hot blue stars, and they're lacking in the formation of new stars, is because when the galaxies that formed that elliptical first merged with each other... Galaxy. I'm misspelling this horribly, but that's okay. Here is a picture of the antenna galaxies. Now, they're called that because there's actually material getting slung off in two directions that are just not in this picture. And in fact, this picture, getting back to the earlier statement, this picture's been doctored. Somebody went in and they used the black paintbrush and they removed and then they blacked out everything else so we could just focus on this without seeing all the other background stars and things. But notice how much pink is going on in this picture, right? These two galaxies colliding has instigated an explosion of new star formation, right? But that's going to use up gas. So when these two galaxies finish their merger, the resulting galaxy is going to be much bigger, but it's also going to be lacking in unused gas that's available for star formation, right? And so once the hot blue stars all die off, we're going to get another one of those amber-colored elliptical galaxies out of this merger. I realize I haven't looked at the chat in a minute, so let me get back to the chat. I'm being congratulated on 100 subs. Dude, I am psyched about 100 subs. Absolutely psyched about it. So thank you for congratulating me on 100 subs. I'm psyched that we have 7 people hanging out right now. Cooper's definitely been talking in the chat. Tom, we got a couple people talking in the chat, but there must be like 5 or so people that haven't said hi tonight, man. And if you're here and you're watching, say hello, man. Let me know you're here. I do know that some people like to project, put this up on their TV and watch it that way and just relax. I've had people tell me that. So I understand why some people who are watching right now aren't actually commenting, and that's okay. But if you can comment, please just say hi. I like to let you know. I like to know that you're here. Well, we've got about 13 or so minutes left in the stream, and I feel like we've really covered the topic of nebulae well. It wasn't my plan for this to be the Nebula episode. In fact, I forgot to rename. Oh my god, I forgot to rename the video before going live. This thing has been called the James Webb episode this whole time. I apologize for the confusion to anybody who's been hanging out with me, who thought we were going to talk about James Webb. Oh man, my boss is saying hi. Nice to see you, Steve. Running short on time, but what causes the different shapes of galaxies? Spiral, elliptical, irregular, etc., and so on. I am running out of time, but I think I have just enough time to cover that topic. What I'm going to do is I'm going to pin that real fast. I'm going to do my housekeeping at the end of the episode, briefly talk about the club. I'm going to try and be quick about it, and then I'm going to spend the rest of my time talking about that. So for those of you who might be joining the show late, again, I am the membership director of the Northeast Florida Astronomical Society. Actually, it should be on this page. And this is our website right here, nefas.org. If you live in the Jacksonville area and you are interested in astronomy, definitely check us out. That is nefas.org for Northeast Florida Astronomical Society. Our logo should appear here any second. It's just taking a bit for this to load. We do have annual memberships. It's $20 for seniors and students, $40 for individuals, $50 for families, which is any 2 adults and whoever they happen to be in charge of. Those memberships, like I mentioned, they are annual memberships, so you pay once a year. You get a nice email from me reminding you that it's time to pay your money. But then you get to be a part of the club. If even if you don't join the club, though, definitely check us out if you like astronomy and you live in Jacksonville, because we do a lot of cool events. Briefly, just going to touch on the fact that you can check out our calendar on the website and see our events there. Cool. Now, with the last 10 minutes, let's talk about galaxy shapes. What causes them? No one knows. Not really, right? This is still an active area of research, and it's really fascinating, and it's something that I'm very interested in. But we do have some clues. There was the Hubble telescope did a live stream, and I attended their live stream. And I used this profile, of course, so that everyone in the comment section saw this channel, obviously. But they did a great live stream on galaxies, and I actually asked a question in the chat about the structures of galaxies, and that is an active area of research, like I mentioned. There's a lot of people working like computer modeling to try and simulate the formation of galaxies in the computer. So it's a little unclear, but I will talk about what we do know. So let's bring up a nice example of a spiral galaxy. We're going to bring up SVA 83 again. We know that a lot of galaxies have spiral shapes, right? This is one thing, obviously. This is what led to the discovery of galaxies, is that people noticed that some of the nebulae had a spiral shape to them, and then they figured out, well, if our whole universe, what we thought was the universe at the time, is a flat disk, and these are worlds that would probably be flat if you viewed them edge on, and some of them were tilted that way, maybe they're other island universes, and that led to figuring out that they're galaxies. But when we look at the spiral shape, right, it is tempting to imagine that these stars are all sort of there, and then as they orbit the middle, they're getting spun up into this spiral shape, twisted up into the spiral. And you would be forgiven for thinking that a star follows this spiral pattern. It moves in this shape, and then, oh no, it crashes into the middle. That's not true. That's not actually what happens. What actually happens is that any given individual star just orbits in a big circle like you would expect. But what happens is, for some reason that I don't completely understand the physics of, but you're welcome to look into it some more, the stars have a tendency to form these sort of higher density regions and lower density regions. So as a star orbits, the stars sort of back up almost like a traffic jam, right? And they clump up and they sort of are more dense here, and then they sort of all separate out again and form a much lower density of stars from one arm to the next. But all the stars will actually go into and out of the arms repeatedly as they orbit, because they are not moving into the middle like you would think. This is not actually circling the drain like you would think. They're just going around in a stable orbit around the supermassive black hole that exists in the center of the galaxy. Because yes, galaxies all have a supermassive black hole at the center. These gigantic black holes whose gravitational pull is what's holding that whole galaxy together. Now, according to Kepler's laws of planetary motion, stars that are further out in a galaxy should be orbiting more slowly than the stars that are in the middle, and in fact, they are somewhat. But the degree to which they should be moving more slowly is wrong. If you graph it out, there's like the expectation, and then there's reality. Actually, no, I think they actually speed up. So what's happening? And the answer there is, this is one of the reasons why we suspect that there's this stuff called dark matter. That there's more material than we know of from the stars, and that this dark matter is itself actually responsible, because there's not enough material to explain the orbits of the stars. They don't make sense. There must be more material there. There's more reasons than that we suspect that dark matter is there. I personally, if you look at some of my older episodes, have a history of being a bit of a dark matter skeptic. But I have to admit that I tend to go with the scientific consensus as a science educator. But I have learned more about dark matter, and I gotta say, I'm getting more convinced, actually, that there really is some material out there that we just don't see. So that's spiral galaxies. But another clue we have, though, is that spiral galaxies tend to be blue, right? And so that tells us that they tend to be young. They tend to be actively forming stars. They have the earmarks of a young galaxy. And the elliptical galaxies have the earmarks of an old galaxy. They're not pink, they're not blue, they're yellowish. So this suggests that in the evolution of galaxies, that there's some tendency to go from spirals to ellipticals, right? This is the idea. But it could be that there are other reasons why ellipticals look the way they do, and there may be some missing information that we don't have. But the general idea now is that spiral galaxies will end up colliding and merging with each other, using up all their gas in those mergers, and then the disruption of two galaxies hitting at weird angles and swirling all around each other causes the orbits of the stars, which is normally when the stars are orbiting, like if they form out of that disk of gas that starts spinning that became the galaxy, that spinning disk of gas is going to flatten out and form the spiral. But once all the stars are formed and then they swirl through each other in a galaxy merger, those orbits of the stars that are all more or less on a plane all get disrupted every which way. And now the stars are orbiting all in different patterns, right? And that chaos just sort of amplifies. He's got a big ball of stars, right? And so that is the elliptical shape that we get. Irregular galaxies are the sort of catch-all term for galaxies. They're just all kinds of weird shapes, and there's a lot of real different reasons for them. First of all, a lot of irregular galaxies are the result of mergers. The galaxies hit each other and they form weird shapes while they settle down. Some of them, like the Magellanic Clouds, are not super big. Really, this is the best we have? Large Magellanic Cloud. Did you mean large? Yes, I did. Here we go. Some of those, like the Magellanic Clouds. First of all, the Large Magellanic Cloud has a bit of structure to it, but is sort of amorphous. The Small Magellanic Cloud. These, by the way, these are little, small, irregular galaxies that actually orbit the Milky Way. Right? If you go somewhere south, you can see them in the sky. They're just not very big, and it may just be that there's just not enough material there to make them conform to one of the normal galaxy shapes, right? We tend to see smaller guys as irregulars. Of course, also our own galaxies kind of messing with them gravitationally. One thing that we often see are bar features. And there's a galaxy called the Great Barred Spiral Galaxy, which really shows this feature. But a lot of spiral galaxies have this feature when you start to look at them, where there's actually a bar of material going through the middle. And in fact, the Great Barred Spiral actually has two bars. There's this bar going this way, but if you look at the core, it forms a second bar going this way. And this was what my question was during that Hubble presentation when I made a comment in the chat, and I said, do we know how the bar feature forms? I've always been very curious. Why would a spiral galaxy, a disk, that I can kind of wrap my head around, why would it form a straight bar in the middle? And it turns out that it's a sort of a density region, but it turns out that what happens is you get stars that orbit and they get slung around the supermassive and thrown out in these big stretched out elliptical orbits. And then there are gravitational influences that will tend to normalize orbits. If you have a bunch of elliptical orbits every which way, if something interacts gravitationally every time those objects hit the low point of their orbit, they get a little kick. It'll adjust the orbit slightly, and they tend to organize together, where all those ellipses will end up lining up. And so that causes all the elliptical orbits of these stars to form these two sort of poles, where they're lined up in these two directions, and the aggregation of all those stars in these elliptical orbits, all at different points in their orbits, all swirling, forms a bar feature through the middle of the galaxy, and then the spirals come off of that. So that's my best attempt to explain how we get the bar feature in the middle of some of these galaxies. So that's my best attempt to answer the question. Like I said, the formation of galaxies and galaxy structure is an active area of ongoing research, and it's a very fascinating one. It's something I find very, very interesting. But excellent question. Glad you asked it, and that's as much as I know about it. With the last 2 minutes, I will remind everybody that I don't hold a PhD. I am not a scientist. I don't work in a lab. I am just some dude. So please, obviously, do your own research on any of the stuff I talked about tonight. Don't take anything I say as gospel. And when I do my best to explain subjects, especially subjects I'm not super familiar with, I try to always be honest about that fact, because I want to be responsible and I want to be intellectually honest about my limitations and what I do and don't know. But that being said, yeah, Scott, I'm with you, dude. Galaxy formation is something that I also find very fascinating. And I often will sit and read, stuff about it, because I do find that, and stellar evolution, if you couldn't tell, the way stars form and live and explode, I also find that super fascinating. But anyway, with the last 2 minutes, I want to say thank you guys so much for watching the show. As always, I am really, really humbled and very, very gracious to have subscribers at all, let alone 100 of you guys, including the 6 or so that are watching right now, and the 1,700 people apparently who watched my last stream after it was posted, because I do post these and people will often watch them later. So a lot of my views come from people watching them later. Although I'm already at 22 views now. Thank you guys so much, man. This channel obviously wouldn't exist without you, and it means a ton that you guys are getting value out of this and that you appreciate it. That said, I post these on Facebook to let people know when they're happening, but I can only post it so far because I only have so many places on Facebook that I can post something. So if you do feel like you're getting a lot of value out of these videos, you really appreciate them, and you think other people would enjoy them, please share. Share the channel with other people. Like, subscribe, hit the bell, all the things that you're supposed to do. And, post about it on Facebook and that kind of stuff. Look forward to it every month, Cooper. I do this every month. But I'm that means a lot to me. I love hearing that you look forward to the show. And yeah, and just share it with people so that more people can know about it, because the whole point here is I hope you can get 50 viewers. Yeah, that'd be cool. 50 people watching at once, man. But yeah, I want people to learn. I just want to share this with people and have people learn. So please help me do that by helping to spread it. So with that, thank you guys so much for attending the live stream, and have a wonderful evening and keep looking up.